Now I want to introduce our first keynote speaker, who essentially is the mastermind of Azure. And Azure is kind of the way we kind of draw boxes around of these things. So Azure is, of course, our public cloud, but Azure, or Azure Stack, is also our private cloud, and the two together form the hybrid cloud. And Azure is also our IoT or edge story with the smaller devices. And so the mastermind behind that is Mark Russinovich, who is the CTO of Azure. He got his PhD from Carnegie Mellon University, and since then has had a very fruitful career with many, many activities. So he's really passionate about distributed systems, about security, about operating systems. He's been working on Windows and Azure, obviously, for a long time, and he has created many tools. So he's the author of the Sysintegration Administration tools for Windows. He had several stints, among others at IBM. But in 1996, he started a company called Winternals, which was eventually acquired by Microsoft in 2006. And since 2006, he has been with Microsoft and has created, essentially, helped create Azure and holding Azure together. One of the very interesting facts about Mark is that he's a very passionate speaker, but also a very passionate author. And he wrote books, not only technical books, but also fictional books, and fictional kind of technical fictional books. And I haven't read them, but I've now I have to 3 books. But I've actually looked, and I'm going to read one of them, and you can look them up. So with that, please welcome Mark Russinovich. Thank you very much.
Thanks, Anna. So I'm really disappointed to hear he hasn't read him. Well, anyway, thank you for having me. It's a pleasure to be here. I want to thank MSR for inviting me to kick this off, Faculty Research Summit. I'm the Chief Technology Officer of Azure. I've been in Azure for 8 years, and in that role, I work on the technical strategy and architecture for the platform. Now, this morning, I've got about an hour with you, and the topic of this session is Azure Architecture. Azure Architecture has grown over the last 10 years since Azure was really started to become a very broad and complicated platform, and so 60 minutes is certainly not enough time to do it justice. I can give you a superficial look at the architecture, kind of the broad brushstrokes, but I thought in the process I'd also share with you insights into some of the collaborations we've had going with Microsoft Research. I think Microsoft Research, in my view, is a competitive advantage we have here at Microsoft, having this research body where people are off exploring sometimes what we think are crazy ideas, but then prove to be interesting. And we actually have incorporated many of these ideas. We've partnered very deeply with them across a number of different projects. And so during this architecture overview, I'm going to weave in some of those projects and show how they've impacted Azure. So Microsoft data centers. Let me talk a little bit about the overall data center strategy, which is to divide the world into geographies. We divide the world into geographies largely based on data sovereignty boundaries. And more we see customers wanting Azure data centers within their country because of the regulatory requirements, data sovereignty requirements of businesses to have the data within the country boundaries. And so this is why we're now at 54 regions worldwide across a number of different geographies. And when we go into one of these geographies, we go in with at least 2 regions. These regions are defined by a latency envelope of less than 2 milliseconds. So going from any data center to any other data center within what we call a region, what we expose to customers, is less than 2 milliseconds. The region pairs, we call them, are 2 regions that are designed for customers to be able to build a disaster recovery solution on top of. Any of our services that support geo data replication are required to support replication between the geo pairs, although they can replicate to other regions as well. The distance between them is typically several hundred miles because we want to place them far enough apart to survive large-scale disasters, so large hurricanes, large earthquakes, floods. But within the region, we actually divide the region into availability zones. Availability zones give customers the ability to create a highly available solution on top of data centers that can fail. So data centers we see can have power outages, they can have local floods and fires, they can also be impacted by other environmental conditions in the area. And so we typically place the data centers that make up these availability zones several kilometers apart at least. The requirement there, again, is that they've got the latency envelope between the data centers that the region has. And less than 2 milliseconds enables customers to build a solution that synchronously replicates data across the data centers, such that a service that uses quorum to commit data, durable data like our storage services or our database service, can replicate the data across 3 availability zones, and that's our minimum that we go into a region with when we light up with availability zones. And then they can tolerate the loss of a full availability zone or the data centers associated with it and still continue to serve write operations. They can actually tolerate 2 and still continue to serve read data off of their service. Now, this is the high-level strategy. I thought it's always fun to take a look at actual pictures of data centers. And so I've got some to share with you just to show you the kind of scale that we're getting to. The amount of capital investment now Microsoft is putting into our data center build-out around the world is on the order of $10 billion, and this is likely to grow. Microsoft Azure has doubled over the last few years, and this is a statement that we make publicly about the compute usage doubling. You can see just our latest quarterly earnings call. We announced 89% year-over-year growth of Azure revenue, and that corresponds to the build-outs that we've got going with these data centers. This one is in Quincy, Washington. Here's another look at that from a different angle where you can see the 8 data centers that I just showed you in the picture there towards the receding horizon, and then you can see another data center here in the foreground. Quincy is a great place because it's served by renewable energy from the Columbia River, and there's plenty of land, of course, there. And we actually offer data center tours there, so sometime if you come to campus, it's about a 3-hour drive out there, but then you can go and take a look and walk through one of our data centers. Here's Cheyenne, Wyoming. This is another area where we've got plenty of land, energy, water to expand, and you can see that we've got massive expansion going on in that area, land being cleared for additional data centers there. This is Dublin, Ireland, another place where we've got massive data centers. There's actually 6 in this picture. There's 3 there on the left and 3 there on the right. It's building out over time, and we'll continue to build new ones there as well. Amsterdam is another site. Amsterdam actually has plenty of great water, very reliable energy. And you can see here we've cleared land for a data center. There's a data center in front of us. That building off to the left looks like it might be a data center. It's actually not a data center. Anybody know what that is? It's a greenhouse, and that means it can be growing 1 of 2 crops, both of them legal in the state of Washington. And then here's another look at Amsterdam. That building that we were looking at is off there on the bottom right. So you can see that this is taken slightly after that previous picture. So those data centers have been built out, and there's more land being cleared for new data centers. Now, one of the projects that we're looking at with Microsoft Research, and this is one, Donald was talking about Microsoft Research's goal is to surprise us, and this one surprised me. When a few years ago, I heard about this Project Natick. Project Natick was MSR looking and saying, hey, can we go build data centers on the ocean floor? And that just sounded crazy to me. And the idea here is we can drop tanks onto the ocean floor. We can cool them with the ambient water cooling that comes with being on the ocean floor and the currents. Actually, the cooling is very efficient because it's already cold down there. And when you submerge them, the other idea is that you can then have them operate for longer periods of time. You can expand them very easily because you just drop additional tanks in the water. And so the first Natick project was announced publicly a few years ago. There was an article actually in the New York Times about it, where we dropped just a single rack in a small cylinder into about 30 feet of water. And we let it sit there for a month, and then they pull it up, and it seemed like things were still working. So we said, cool, on to the next phase. And this next phase is one that we just announced about a month ago. This is a look at the cylinder here. It's about a little over 12 meters in length, about 3 meters in diameter. It has 12 racks that are 42U height in them. And in this build out, we've got about 1,000 servers. They're decommissioned Azure servers. Of course, the storage has been pulled out and shredded on the way out of the data center, and so there's new hard disks and SSDs here, but they are the actual same servers that we've been operating in our Azure data centers. The tubes are built actually at a facility in France that builds submarines, and they're very good at building these underwater technologies. It takes 30 days. It took 30 days from the finalization of construction at the plant in France to this being online at the bottom of the ocean floor. So that shows you the kind of agility that we might get out of this. Expanding capacity when you're doubling year over year is a tough problem, and if we can just simply expand on demand wherever we need to by simply shipping a new tank out and having it deployed within 30 days, that will let us meet that demand very efficiently. This particular experiment has been done off the Orkney Islands in northern Scotland. The tank has been shipped out to about 1 kilometer offshore and then submerged into about 100 feet, 36 meters of water. And then you can see some pictures here of it being dropped. Now, one of the benefits of this, so kind of constraints and kind of interesting problems that we're looking at here as part of the research is when the racks are put in that tube, all of the air is sucked out of it, and all of the vapor is sucked out of it as well. And both of these contribute to corrosive effects on the servers. Further, once the tube is dropped, it is in a fail-in-place mode, which means that as the servers and components fail, we simply let the system degrade. And once it's become degraded enough, what we do is bring another tube, another replacement, drop it in the water, and then decommission, migrate the workloads and data off of the one that's degraded onto the new capacity. And so a very efficient way to manage the servers inside. The idea being that the servers will last longer, so our average server lifetime in a data center is roughly 4 to 5 years. So we think this can extend the life cycle of those servers because in addition to the lack of corrosive effects on the servers, there's no maintenance going on. And maintenance disturbs the servers, which can cause problems as well. The PUE that we get out of this, so if you take a look at the typical advanced state-of-the-art data centers on land that are designed with traditional technologies, the PUEs are up in the 1.1 plus range. The PUE that we expect on this is about 1.03. So this offers, like I said, a bunch of potential advantages, including the energy efficiency that we get out of this. Now let me take a look at Azure networking now. And so if you take a look at Azure networking, it's actually a very broad set of services and technologies. You can see some of them listed here by different categories. For example, over in the DC hardware space, we've got specialized network hardware, including open source software that we're putting on our switches that we released to the Open Compute project. You can see we've got a bunch of different services that are available to customers. The core one is virtual networks. Virtual networks are what the abstractions that customers bring and layer IP addresses on top of to connect their VMs to their virtual machines together and connect them with our Azure services. And then you can see we also, as part of that network topology, allow connection from outside the data center. One of the examples of a service that we make available to IT customers is something called ExpressRoute, which gives them private connections into our dark fiber backbone. That gives them high SLAs, up to 100 gigabits in dedicated bandwidth into our backbone, and they don't have to then rely on the ISPs and the flakiness of the open internet. Speaking of that dark fiber backbone, we've got one of the largest networks in the world. We've got about over 30,000 miles of fiber spanning the world. You can see a map. This isn't necessarily up to date. This is a few months old. But you can get an idea of the kind of global coverage we've got, including subsea cables that we've laid ourselves. One of the examples is one from Bilbao to Virginia called Maria that we launched a couple years ago. One of these subsea cables is a massive capital expense. We went into it with Telsus and Facebook, but all three of us recognizing that the existing subsea cables connecting Europe and the US almost all go from England to New York. which causes a potential single point of failure. So in addition to building out an additional 150 terabits of capacity between Europe and the US, this gives us some redundancy with respect to those failure points of the existing cables that you can see up there. We've also launched another subsea cable connecting Asia and the US as well recently. In addition to the dark fiber, we also have 4,500 peering locations to connect with other networks around the world, including ISPs. And then we also have 130 edge sites. The edge sites are where we deploy our own software and servers, where we can cache software and we can run compute on the edge, do SSL termination, and give customers that are using our cloud services a better experience. We expect those point-of-presence sites to also be part of our third-party edge strategy going forward, so we're looking at that. Now, one of the aspects of networking, I just focused on the physical aspects in this previous slide, is that networking in the cloud is what's called software-defined networking. And what many of you probably are aware of this, software-defined networking became something kind of well-known about 5 to 7 years ago. We had companies being bought for $1 billion because they were developing software-defined technologies. The idea here is if you take a look at traditional IT networking, it's been an appliance model where multiple layers of this networking stack are combined into the single appliance. Those layers are the management layer, which takes commands to configure and deploy networks in the data center. The control layer, which actually takes those abstractions that are exposed as APIs and actually translates them into things like ACLs and routing rules. And then the data plane, which is programmed with those ACLs and routing rules to honor what the control plane decides. And the data flows through the data plane, of course. With software-defined networking, we take those and spread them out, and we implement them all in software, at least mostly in software. I'll get to a caveat on that in a second. If you take a look at the way we've done this in Azure, the layers are the Azure Resource Manager, which is the universal control plane for all of the Azure APIs. If you talk to compute, if you talk to storage, if you talk to Cosmos DB, on the control plane to create resources and to configure them, you're going through Azure Resource Manager. So when you create a virtual network, you go through Azure Resource Manager. Azure Resource Manager hands that off to the network resource provider, which implements those APIs. And then that calls into network services that are controllers to go and set up and define those virtual network ACLs and routing rules. And then it talks to agents on the servers or the hosts to implement those rules. The idea here is we want to push as much logic down. The advantages of software-defined networking are kind of obvious here. We're not paying for expensive proprietary appliances, which have reliability issues. They've got scalability issues. What we've got here is cloud-native layers of the networking stack from the top to the bottom that we can expand, that are highly available, that can tolerate massive failures, including failures of availability zones, and are much cheaper to operate. Now, if you take a look, I just mentioned kind of Azure, the software-defined networking stack in the context of Azure networking. You can see the layers here of the whole Azure architecture at a very high level. Up at the top there on the far right, you can see the Azure portal, the command line interface. These are, and the SDKs, which talk these management APIs, these control plane APIs, to Azure Resource Manager. And then you can see some example services plugged into Azure Resource Manager. We call those resource providers, like I just mentioned. Then beneath that, you've got the Azure Fabric Controller, which is responsible for launching virtual machines. Everything except for a few services at the very bottom of our architectural stack runs in virtual machines, including things like Azure Database and Cosmos Database run in virtual machines. There's a hardware manager that manages the lifecycle of servers and health of the servers, and then the hardware infrastructure underneath. And then you can see that there's authentication, role-based access control, telemetry systems that span the entire software stack. Now, if we focus just on the networking part of this is kind of a zoom in on what I was explaining earlier. We've got Azure Resource Manager, the network resource provider, and the compute resource provider. There's no network without compute. And so these work closely together. They work closely together because a customer says, I want to define a virtual network, and then I want to place a virtual machine into that virtual network. The job then of the system is to go find a computer to put that virtual machine on, and then join that to the virtual network. And so what you'll see is that these components all meet down on the server, each talking to their own agents. There's a network agent down on the server. There's a compute agent on the server that launches a virtual machine. The network agent then plumbs the IP addresses and routing rules into that virtual machine to have it join this virtual network. So another area where we've collaborated with Microsoft Research, and this one goes back to a project that started in MSR about 2010. One of the MSR researchers, Doug Berger, who now is part of the Azure team in the hardware group, he had this vision that FPGAs had a role in the modern data center architecture. Now, FPGAs have come and gone throughout time, and they fell out of vogue for over a decade. Doug believed that they had a place, and he took his vision to Bing and started a project with Bing to see if they could accelerate the indexing of Bing content on FPGAs. That project pilot was successful and then deployed into production in Bing. Now, we faced an issue in Azure about 5 or 6 years ago where we saw networks going from 1 gigabit to 10 gigabit on the servers. We saw 40 gigabit coming, 50 gigabits coming next year, 100 gigabits around the corner. And when we took a look at us processing that amount of data on the servers themselves, on the compute servers, on the CPUs, we realized that we'd be burning large amounts of those computers just doing nothing but packet processing. So the question is, how could we do this more efficiently? And how could we keep up, not just with the bandwidth, but keep latency low for that amount of data processing? Our network engineers found out about the Bing project. Doug found out about our problem, and we started to collaborate together on something called accelerated networking. The idea here is that we take those FPGAs, and just a quick refresh on FPGAs for those of you that might not have been around for those previous phases or just know it from the acronym there. There's small devices with thousands, tens of thousands of logic elements, typically DSPs on them, interfaces to the PCIe bus, USB controller. And the idea here is that the interconnect between them is dynamically programmable. Within a very short period of time, within a few milliseconds, you can program the interconnects between these. And what that allows you to do is create a reconfigurable topology. These kinds of devices, because they're so much redundancy here of the same kinds of computational elements that can be programmed, are great for highly parallel workloads. And packet processing is a highly parallel workload. So looking at these, we said, hey, maybe we can plumb the SDN stack into an FPGA, effectively getting close to hardware ASIC performance, but with the flexibility of being able to update the algorithms and the software-defined networking as we go. In fact, we have added many, many features, dozens of features just in the last couple of years to our software-defined networking stack. So we absolutely need that flexibility. We cannot burn the software-defined networking algorithms into ASICs because that would just not allow us to let the network at large evolve. So what we did is figured out how to plumb the networking stack into the FPGA so that in the previous slide where you talk about the networking agent on the servers, getting those control plane rules for ACLs and for routes and for IP addresses, it plumbs those into flow tables that are implemented in soft logic on those FPGAs. And you can see the comparison as we moved into accelerated networks. We started deploying FPGAs into every single server about 3 years ago. So we're now, we think, have the most deployed FPGAs in production of any company in the world. The left side of that slide shows you the software architecture where we're processing those packets on the host, on the servers. And you can see there's a lot of software layers that we've got to go to. On the right side, you can see we bypass all that, allow the virtual machine to talk directly to a network interface that's virtualized and provided directly to that virtual machine so that they can just talk directly to the hardware. And so there's no computational resources other than some control plane operations on the CPUs. That frees up the CPUs, of course, to do more useful things like actually run virtual machines instead of process packets. So I'm going to show you a quick demo of the comparison between those two different technologies here in action. And first, I've got two virtual machines here that I've got without accelerated networking turned on. Accelerated networking is available in all virtual machines around the world in Azure. It's an opt-in currently, because we wanted to make sure that there were no compatibility issues with operating systems that customers use. And so right now it's opt-in. Soon it will be opt-out. But on this virtual machine, I have it opted out. What I've done is just set up a receiver with a program called SockPerf. Here's another virtual machine also opted out that will talk to that other one and send it packets as quickly as it can. And what we're going to see after about 15 seconds of run is the latency that these two virtual machines experience talking to one another over that software-defined networking stack as they're implemented in the host. And so you can see the latency, it's about 200 microseconds, which isn't bad, but let's go take a look at what accelerated networking can give us. So I've got here another program, and this is using something called DPDK on a Linux VM, which allows the Linux kernel to process packets extremely fast with very low latency. So we're going to see something that looks a little bit better. So that's 10 microseconds. And so we see typically latencies between 5 and 10 microseconds as compared to about 200 microseconds on a software-defined stack. Again, with almost no CPU usage on that versus the software stack. Okay, let's switch back. All right, so let's talk a little bit about servers now. And I'm going to take you on a tour of history here to show you the evolution of servers in the cloud. Because it's kind of interesting, back when I started in Azure, the whole premise of cloud was cheap commodity scale-out servers. Scale-up was anathema to cloud. But watch what happens. Here's our Generation 2 servers that we launched Azure with in 2010. They're 2-socket Opterons with 6 CPUs on each socket, so a total of 12 cores. Has 32 gigabytes of RAM in it, has a 1 gigabit network adapter. I'm going to quickly move through these. Gen 3, we jumped to 10 gigabits. Here's our HPC SKUs we started to introduce. What we did here with our HPC SKUs, which we still have, is InfiniBand, 40 gigabit InfiniBand networking, which offers latencies that are even down to 1 to 2 microseconds as opposed to what we see there. By the way, that was TCP over InfiniBand. It's, of course, a different type of network protocol that's not TCP compatible. Here we have our Gen 4 servers. You can see that the amount of RAM that we're starting to deploy is larger. There's more CPUs, and this lets us pack more virtual machines onto the same servers. Then we introduced something called Godzilla, and here's the first example of a massive scale-up. This was about 3 years ago. And what we saw are customers starting to migrate large in-memory databases to the cloud. Specifically, SAP HANA, one of the core workloads in IT, is a scale-up in-memory database. And they needed very large virtual machines to be able to support the kinds of computation that their enterprises ran on. So we introduced this. It's called Godzilla. It has 512 megabytes of memory, so the largest virtual machine in these has 450 megabytes of memory, or gigabytes, sorry, of memory. Sorry, not megabytes. Here's our Gen 5.1. So this is what we've been deploying for the last few years. Then you can see we have started to introduce GPUs, and these are NVIDIA GPUs, V100s, P40s. And then we introduced this about 1.5 years ago. This we called Beast, and this one, again, customers migrating even more and larger SAP workloads to the cloud, including Microsoft IT. We needed even larger virtual machines. This one has 4 terabytes of RAM in it, has 144 processors in it. And so this now is what we've got currently in production as our largest VM size. You can see our Gen 6 server. This is what we're deploying right now into production. And you can see it's got 768 gigabytes of RAM in it. So we continue to rise up in RAM and CPUs. And what we just announced about a month ago is this. We call it Beast V2 internally, but I think we should call it Mega Beast. This thing has 12 terabytes of RAM in it. And so we're the first public cloud to announce support for 12 terabyte virtual machines. And that, of course, SAP workload unblocking as they move to the cloud. So not quite commodity scale out anymore. All of this is built on top of an open source platform called Project Olympus. Project Olympus is designed to be extremely flexible, to support high-density storage, to support SSD, hard disks, also to support all the different kinds of processor technologies we want to put into the cloud, including AMD, ARM, as well as Intel processors. We also support NVDIMM, so we support batteries in these servers that power RAM so that we can tolerate a power outage, but treat that RAM as non-volatile, being able to write it out to flash before the server completely loses power. And this is designed to go to 50 gigabit NICs. Like I said, we're already looking at 100 gigabit coming at us. Project Olympus actually is open. We contributed to the Open Compute project, so anybody can go look at these designs and build their own servers. The idea is being that we innovate with the ecosystem. In fact, Olympus Gen 6 was the first version of our server design that we actually took the initial design out, made it available publicly, and sought feedback from all our hardware partners. And so they all made contributions back into it that were then eventually made it into the final Gen 6 Project Olympus platform. Now, we're also looking at introducing specialized hardware into our data centers. We've done things like we've announced Cerberus, a specialized security coprocessor that we put into our servers. But another place that we're looking at is accelerating deep learning. This is another project led by Doug Berger, focusing on the use of FPGAs for deep neural networks. And his idea here is, again, machine learning technology is changing very quickly. So instead of burning topologies into ASICs and having them be static and rigid and have short lifetimes, if we could leverage FPGAs, we could adapt to new algorithms as they come up, new topologies. So the first version of this is called Project Brainwave, and we released this publicly into public preview at Build earlier this year. The idea here, of course, is that we can plumb these DNNs into FPGAs. These FPGAs are on servers that are connected with a low latency network, and so we can actually take very large DNNs that don't fit into a single FPGA and deploy them across multiple servers to have them operate as basically a hardware as a service microservice platform. That's Doug's vision. Now, what we've done, I'm going to talk a little bit about one of the specific use cases here, and that is something called AI for Earth, collaboration between us, Esri, and the Chesapeake Conservatory to go look at land and evaluate how it's changing with respect to climate change and other factors. Traditionally, this has been done by humans, and satellite imagery is captured, and then humans go and look at these images and decide how much forestry, how much water, how much urban space is in the image. And then they track that over time. So hundreds of hours, thousands of hours spent by humans up to now on this. Now with Brainwave, we can take those images. The first algorithm neural network that we programmed into Brainwave is ResNet 50. It's a customizable ResNet 50 where the customer can train their own model as the final layer and then package that up even and deploy it on an on-premise Brainwave. But it's deployed as a service in Azure. Once the customer trains their model on top of ResNet 50, they deploy it into Brainwave VMs and then can access it via an API. And that's exactly what this has done, this pipeline shows you. I'm going to switch to a demo to show you Brainwave in action. Oops. So first I'm going to show you this Explore land cover classification, which will show us, if I just select one of these, it's going to execute it on Brainwave and inference. Now Brainwave can do inference of an image in less than 2 milliseconds. And it can drive throughput up to 40 teraflops, tera operations, off an FPGA device, even at batch size of 1. So this is what we call real-time AI, something that's differentiated from other traditional batch-oriented devices like a GPU, where you've got to feed in 100, 200 images at once to get that kind of throughput out of the device. Now, here's the AI for Earth app. And what I'm going to do is process these images using CPU. You can see the CPU's processing about 6 a second. Batch-oriented GPU, about 60. You can see that its progress down here as it classifies those images. And then here's Brainwave. And then, like I mentioned, we can scale up Brainwave. So here's Brainwave with roughly 800 FPGAs. So the total data set for the US is about 195 million images, 20 terabytes of data. With Brainwave, we can process it in 10 minutes, the entire data set, for a cost of about $43. Okay, let's switch back. So let's talk a little bit about compute now. And here's that high-level Azure architecture diagram that I showed you earlier. What we're going to focus on now is the compute stack, and specifically how we deploy multiple workloads down onto the platform. The Azure Fabric Controller, like I said, is responsible for launching virtual machines. But that's typically not the way that customers using cloud-native technologies will interact with the platform. They will, of course, use virtual machines to migrate their existing IT workloads in a lift and shift motion. But if they're building something cloud-native, they're going to be using containers and container orchestrators. So that's what you can see here. A couple of container orchestrators, kind of the ones that we have bet on. One is called AKS, Azure Container Service, which is Kubernetes as a service, Kubernetes being the open source container orchestrator. It's open source. It was developed at Google by 3 people. In fact, one of them, Brendan Burns, actually works in the Azure Compute team. So Azure, we leverage open source a lot, we contribute to open source a lot, and we've gained a lot of credibility with the open source community, enough that people can leave, well, oftentimes we see people wanting to leave Google to come to Microsoft to work on open source technologies. Kind of something that is shocking for people that have watched Microsoft over the last 2 decades. Now, the other service you can see here is called Service Fabric. This is one technology we developed internally, and that most of our cloud services are built on top of. Most of the Azure infrastructure is built on top of this microservice platform, which can also do container orchestration. But it's unique in that it supports stateful services. So it's tightly integrated, its federation model, its health model, to be highly scalable and to support the highly durable storage of data. And when you take a look at a service like Cosmos DB, which is built on top of this, Cosmos DB is replicating data, three copies of each database. And so with tight coordination with the Service Fabric controller on health, on upgrades, Service Fabric can make sure that that data is always available for right operations in the face of failures and reconfigurations. And Service Fabric is something that, if you take a look, actually, let me back up here, and I'll come back to Service Fabric in a second. A deeper dive into, I thought I'd show you just the complexity that we've gotten to in the orchestration of something that seems as simple as deploying a virtual machine in the cloud. Here you can see all of the resource providers, or at least most of the resource providers, and some of the services, regional services that are involved with the deployment of virtual machine, which includes compute, network, and storage. And you can see we've got the idea of clusters down, clusters with cluster managers that manage groups of servers. So tenant manager, that's TM. Data center manager manages the hardware for a cluster. Network service manager, software load balancer. All of those are basically cluster level services. They manage a slice of an entire data center or region. And then down on the servers, we've got agents corresponding to each of these. And when we deploy a virtual machine, here's the kind of flows that you see of these services talking to each other, communicating data, so that we can finally end up with a virtual machine down on a server that has a network and storage attached to it. But going back to Service Fabric, which is layered on top of this, where the world is going is something called serverless technology. So we went from containers a few years ago, which was all the rage, then to container orchestrators, then microservice platforms and PaaS on top of microservices. And then now what we see is the next level of abstraction and productivity, which is built on top of serverless technologies. Serverless, really pioneered by functions as a service. We have got our own functions as a service called Azure Functions. The idea here being the developer just writes a piece of code, they give it to the cloud platform, and we take care of everything else. We take care of auto-scaling, we take care of the reliability of it. They focus just on the code, and they pay for only the resources consumed by that piece of code. So they specify, I want this much RAM for this code, and we bill only for the amount of CPU consumed by the code. So if the code never runs, the function's registered, nothing ever happens. They don't get charged anything. If 1,000 invocations of that function happen and they each run for a minute, then they get billed 1,000 compute minutes. And so it's pay per use and really great for bursty type of workloads. It's also an event-driven model that is now becoming very popular in the cloud. Each of these functions is triggered by some event. For example, some image being dropped into a storage account could kick off a function that then calls into Brainwave to go do inference on that image. But what we've got with Service Fabric is we're taking that serverless concept and expanding it to general purpose microservices, to general platform, not just event-driven microfunctions. In this case, we just announced the public preview of this service, Service Fabric Mesh. And Service Fabric Mesh is serverless Service Fabric. So you can actually take a description of a microservice application. It's even stateful, built with even abstract programming models like the actor model, and give it to us, and we will go and launch it on, we'll take care of the provisioning of the virtual machines, we'll launch those containers onto them, and then you get paid only for the execution of those containers and never have to worry about the infrastructure, only focus on the containers. And so this is where the world is going, is this kind of developers only worry about their code, and the platform takes care of everything else. We're at the next phase of this, and there's still a lot of work to do in this. Now, to highlight one of the very productive collaborations we've had with Microsoft Research, we've been collaborating with Microsoft Research on the problem of resource allocation in our data centers for since close to when I joined Azure, about 8 years ago, including Microsoft Asia, one of the key researchers there. In fact, we hired him into Azure about 1.5 years ago. He was instrumental in this. The collaboration with Microsoft Research continues on this project called Resource Central, which is generally looking at how do we make use of resources in general more efficient. And that efficiency comes in a number of different forms. How do we pack virtual machines more tightly and not waste resources on servers? How do we make sure that an evictable workload doesn't interfere with the placement of a non-evictable higher priority workload? How do we make sure that we don't exceed power budgets in our data centers as CPU spins up? All of these are questions that we want to get better insights into out of Resource Central. And if you take a look at Resource Central, it's heavily dependent on machine learning algorithms, taking in data, historical data from production, training on that data, and then generating models that we then deploy as offline services that are integrated with the online resource allocator. And they're offline in the sense that the running system does not depend on the availability of those services. These are optimizations. One of the principles in the cloud is you want as few dependencies on the runtime operation of the service as possible, because failures always happen. And if there's a non-critical component, you don't want to put that in the hot path. But you can look at the problems that we're looking at. Virtual machine scheduling, which clusters virtual machines go to. I mentioned power over subscription, how we do server maintenance in an efficient way without impacting customers or minimally impacting customers. And then even giving customers right-sizing recommendations based on looking at the historical patterns of other virtual machines that they might be running, other ones that are running similar workloads, their historical usage of resources by that particular virtual machine. We can say, hey, looks like you could easily fit into a virtual machine that's much smaller, or you need more resources actually because you're bottlenecked. Here's just one example of one of the projects that we've had ongoing. And I say ongoing because these are never kind of ending projects. There's always room for more optimization. And as Donald mentioned, 1% of optimization in the right place can have huge impact. When you're talking about millions of virtual machines and you're talking about millions of servers, saving 1% of your resource can literally mean millions of dollars. And so this resource allocation algorithm that we've developed with MSR assigns each resource dimension, assigns it a weight, which is relative to the scarcity of that resource, and then runs this optimization problem where we try to maximize the availability of those scarce resources through our allocations. You can see there on the right 2 example allocations. Obviously, the one on the right is a better one for this particular server. If we allocate 2 low memory machines, meaning they consume a lot of cores but little memory, we waste a bunch of memory on that server. But if we take one of those low memory machines, take another one that's not consuming as many CPU cores, so we've got additional CPU cores there left for a virtual machine that is a high memory virtual machine, few cores relative to the amount of RAM, we can actually make use of all the resources on that server. So that's just a simple look at the optimization problem. Here's another example where we take a look at historical eviction patterns for virtual machines and use them to influence the allocation algorithm. So we've got two virtual machines, A, and we know B is going to be coming. B is a full server virtual machine. A is a 1/4 virtual machine. And there's two servers that we've got to pick from to allocate this. Both can fit this virtual machine A. And the question is, which of these is the better fit if the probability that a virtual machine is going to terminate by time t when we need to allocate virtual machine B is 1/2. And you can see the probability if we deploy that virtual machine A on node 1, well, the probability of it terminating, those two VMs that are then on node 1 terminating by time t is 1/2 squared. The probability of one of those three virtual machines, all three terminating on node 2 to make room for that virtual machine B is 1/2 to the third. And you can see that, so the probability at time t that we'll be able to allocate virtual machine B is 6/16. But if we place the virtual machine on node 2, our odds get better that virtual machine B will find a home. So that's another example of the kind of resource allocation strategies that we've developed in conjunction with MSR. And you can see we've used a bunch of different machine learning algorithms depending on the problem. For CPU utilization modeling, random forest, for lifetime of the virtual machine, gradient boosting trees. And the accuracy of these models as we develop them is extremely high. High enough, of course, that they are having a significant impact on our efficiency in the data center. So let me now switch to Azure Storage. In Azure Storage, there's 3 layers in the architecture, roughly. So you can see the front ends there. You can see a partition layer, which partitions the data, and then you can see a distributed file system layer, which handles what are called streams for those partitions. And that layer is the one that actually does the replication. The others are effectively the control plane, and the DFS layer is the data plane for the storage service. On top of this, we've got load balancers, and then the storage service exposes a number of different APIs. It exposes a simple blob API in both block blob and page blob forms. Page blob is something that we use for virtual machine hard disks, so page blobs are fixed. The page is fixed in size. A block blob is arbitrary size. Queues, which are simple FIFO queues. File API, which it includes SMB as well as HTFS, we recently announced as well. And these storage services support replication across regions. So if you deploy something with regional geo-replication, RAGRS, then what you've got are the partition layers doing replication. Now, like many of the pieces of Azure that we started with 10 years ago, we've had to re-architect the system as we've gotten to larger and larger scale. The initial storage architecture was based on these storage stamps, or clusters, a fixed number of physical servers. And what you've got when you've got a large data center or region with many, many stamps is inefficiencies. Inefficiencies and scale limits. The scale limits are the limits of the servers in that one stamp, are the maximum limits that we can offer customers for throughput and size of their storage service. And then it's inefficient in terms of the fragmentation, because we've got to have failure buffers in each cluster, we've got to have expansion buffers in each cluster, and we can't amortize those buffers across all of the servers in the data center or region. So we started re-architecting the storage system about 2.5 years ago, 3 years ago actually. And we just are putting this into production now. This is called Gen 2 Azure Data Lake Storage. And we call it internally limitless storage, because if you take a look at some of the scale limits, so a storage account limit, and we're going to see these limits even go up, 50 gigabytes per second as opposed to the 60 megabytes per second that we used to have. The throughput spikes are instantaneous, and there's no warm-up for these. And the scale we can effectively, our target is that one storage blob could consume every single byte of storage in an entire region. That's the kind of scale limits we're going to. So basically, that's hence the name limitless. You can see that the throughput now that we can drive off of being able to take advantage as a much scale-out storage as servers as possible in this architecture. We can go from uploading a 5 terabyte blob that used to take 14 minutes to uploading one, in 14 minutes that previously took, you can see, 12 hours. So massive improvement in the kind of throughput that we get with this new architecture. But we're also looking with MSR at the future of storage. We've got hard disks, we've got SSDs, we also have tape now, and we've got also something called Pelican, a project where we've got hard disks in basically hard disk appliance form, a rack of hard disks where only some of the hard disks can be spun up at a time as a low-cost archival storage solution with higher latency than a single hard disk solution. But we want to do better. It's all about maximizing efficiency, especially for archival storage, which can be around for long periods of time without ever being accessed. You want that to be as cheap as possible. The world is now storing massive amounts of data. And so we've got two projects going on with MSR. One is called Silica, and it's looking at glass, and I'll explain that one. Another one's called Palix, and it's looking at use of DNA to store data. I don't have time to talk about Palix this morning, but that's another very exciting project that offers the promise of storing a full zettabyte of data in a single rack in a data center. And just to put that into perspective, the estimate is that there's around 20 zettabytes of data on the planet today. So 20 racks and you could store all the data in the world on Palix. But going to glass, let me talk a little bit about this. This is a project with the University of Southampton, collaboration with MSR Cambridge there and us in Azure. Idea here is to store data in glass, obviously. Now, that might seem straightforward, just etch the data into the glass. The problem is, up to now, there's been no way to efficiently store data at high density in glass, because whenever somebody tries to etch it with lasers, they end up with defects. The defects caused by material deformations because the laser pulses are damaging the atomic structure of the glass. And so you might write something, but you can't read it back. So what the University of Southampton and Microsoft Research have been working on are using high-speed lasers that operate at the femtosecond range, which is the same kind of pulse duration that you might have cataract surgery with, or lens surgery. And how long is a femtosecond? It's really short. I had to look it up. And with a femtosecond laser, we can pulse and generate what are called voxels in the glass, which are three-dimensional structures you can see here that have some depth. And by targeting the laser at different depths in the glass, we can create multiple layers of this in one piece of glass. In fact, I was given a sample yesterday by the Project Silica team that has 76 layers in it. So we've gotten now where we can store very efficiently vertically as well as horizontally with 5-micron separation between these voxels. And here's a look at the reader for this. The interesting thing about glass is once you write it, you never have to refresh it. It lasts for literally millions of years, longer, or billions of years really. So outlasting even probably the Earth. And you don't need a specialized reader. You don't need a specialized reading technology to read it. All you need is light. So flashing light on this and looking at the reflections of light, or how that light is diffracting off those voxels, you can read the data off of it. And so this is an early look at a read head. You can see that this one is going through 20 layers, showing a simple image of those 20 layers. So each of those depths. And then here's a look at how we decode the data. We take multiple images, add a layer, using different conditions. And then we look at the retardance and orientation, and then map that to orientation and retardance, where we can encode data in those two values. And you can see here an example of a 3-bit per voxel example of encoding data on that glass. What this promises in terms of density, too, is storing about 50 terabytes of data in 2 centimeters squared. So this is orders of magnitude more dense than the kinds of archival data that we have out now. This would be a huge breakthrough for archival storage. And it's one of those long-term kinds of projects we've got at MSR. It's multiple years, significant amount of investment, of course, in material technology and equipment that needs to be taken from a lab prototype and then made data center production ready. And we're all doing it in collaboration. So that brings me to the conclusion of the talk. Here, I gave you a brief overview of high-level Azure architecture, a look at some of the interesting MSR projects. The bottom line is that when it comes to research in the cloud, besides, of course, innovative programming models, innovative topologies, communications architectures, much of the research that we focus on is driving up efficiency and scale and performance. And you can look at the projects that I showed you. They're all aimed at efficiency, scale, and performance. They're just some of the projects that we've got going with MSR. I mentioned Palix. We've got another one, optical networking, called Sirius. We've got another one that you're going to hear about here if you go to Albert Greenberg's talk on CrystalNet, which is simulating our wide area network so that we can make configuration changes safely. The list goes on. And it's, like I said, it's a competitive advantage of us to have MSR here to go out and explore these kinds of areas. In some cases, ones that seem far-fetched to us when we initially look at them, and offer a bunch of research problems like Project Natick that, if they're realized, could really transform our business. So with that, I want to wrap it up. Again, I want to thank Eric and Donald and Dan for inviting me to open up this faculty summit with you. I hope you have got a fantastic few days here, a bunch of interesting talks you've got ahead of you, and thank you very much.
Thanks very much.